This a big mess because I'm super sleepy in the morning, and every day I have all kinds of stupid problems. But I'm used to my life is like been like that many years. But just be this will just be a long video. So I'm just continue in next video. Yes, read to the end of the documents.
Zilog Z80. Zilog Z80 Zilog Z80.jpg. A Z80 manufactured in June 1976 according to the date stamp General Information launched March 1976 designed by Federico Fagin Masatoshi Shimokaman manufacturer, S. Mostek Cinetech, Zilog SGS Thomson NEC, Sharp Toshiba, ROM Gold Star, LG, Hitachi, National Semiconductor, I, and others. Performance Max. CPU clock rate 2.546 EMSTO 10 MHz with CMOS variant up to 20 MHz and binary compatible derivatives. From Zilog, up to 33 and 50 MHz. Data width 8 bits, 1. Address width 16 bits, 1. Physical specifications transistors 8500, form process. Package, S, 40-pin DIP. 44. The Z80 is an 8-bit microprocessor introduced by Zilog as the startup company's first product. The Z80 was conceived by Federico Fagin in late 1974 and developed by him and his 11 employees starting in early 1975. The first working samples were delivered in March 1976. And it was officially introduced on the market in July 1976. With the revenue from the Z80, the company built its own chip factories and grew to over 1,000 employees over the following 2 years. 2. The Zilog Z80 is a software-compatible extension and enhancement of the Intel 8080 and, like it, was mainly aimed at embedded systems. Although used in that role, the Z80 also became one of the most widely used CPUs in desktop computers and home computers from the 1970s to the mid-1980s. 3. 4. It was also common in military applications, musical equipment such as synthesizers, like Ev Roland Jupiter 8, and coin-operated arcade games of the late 1970s and early 1980s. Including Pac-Man. Zilog licensed the Z80 to the US-based Cinetech and Mostek, which had helped them with initial production, as well as to a European second source. Manufacturer, SGS. The design was also copied by several Japanese, East European and Soviet manufacturers. 2. This won the Z80 acceptance in the world market since large companies like NEC, Toshiba, Sharp, and Hitachi started to manufacture the device, or their own Z80 compatible clones or designs. In recent decades Zilog has refocused on the ever-growing market for embedded systems and the most recent Z80 compatible microcontroller family. The fully pipelined 24-bit Z80 with a linear 16 MB address range, has been successfully introduced alongside simpler Z80 and Z180 products. Contents. History. Design programming model and register set registers. Microarchitecture. Z80 assembly language data point 2200 and Intel 8008. New syntax. Pin PLCC, 44-pin QFP. Socket, S. Not applicable. The Z80's original DIP40 chip package PINUT instruction set and encoding undocumented instructions. Bugs. Example code. Instruction execution. Compatible peripherals. Second sources and derivatives. Second sources. Derivatives. Notable uses: desktop computers, portable and handheld computers, Embedded systems and consumer electronics. See also. Footnotes. References. Further reading. External links. History. A May 1976 advertisement for the Zilog Z80 8-bit microprocessor. The Z80 came about when physicist and engineer Federico Fagin left Intel at the end of 1974 to found Zilog with Ralph Ungerman. At Fairchild Semiconductor, and later at Intel, Fagin had been working on fundamental transistor and semiconductor manufacturing technology. He also developed the basic design methodology used for memories and microprocessors at Intel and led work on the Intel 4004, the 8080 and several other ICs. Masatoshi Shima, the principal logic and transistor level designer of the 4004 and the 8080 under Fagin's supervision, joined the Zilog team. According to the designers, the primary targets for Z80 CPU, and its optional support and peripheral ICs, 3, were products like intelligent terminals, high-end printers and advanced cash registers, as well as telecom equipment, industrial robots and other kinds of automation equipment. By March 1976, Zilog had developed the Z80 as well as an accompanying assembler-based development system for its customers, and by July 1976, this was formally launched onto the market. 5. Some of the Z80 support and peripheral ICs were under development at this point, and many of them were launched during the following year. Photo of the original Zilog Z80 microprocessor design in depletion load NMOS. Total die size is 3545 3350 m. This actual chip manufactured in 1990. A CMOS Z80 in a quad flat package. Early Z80s were manufactured by Cinetech and Mostek, before Zilog had its own manufacturing factory ready, in late 1976. These companies were chosen because they could do the ion implantation needed to create the depletion mode MOSFEs that the Z80 design used as load transistors in order to cope with a single 5-volt power supply. 4. Fagin designed the instruction set to be binary compatible with the Intel 8080, 6, 7, so that most 8080 code, notably the CP/M operating system and Intel's PL/M compiler for 8080, as well as its generated code, would run unmodified on the new Z80 CPU. Masatoshi Shima designed most of the microarchitecture as well as the gate and transistor levels of the Z80 CPU, assisted by a small number of engineers and layout people. 8, 9. CEO Federico Fagin was actually heavily involved in the chip layout work, together with 2 dedicated layout people. According to Fagin, he worked 80 hours a week in order to meet the tight schedule given by the financial investors. 2. The Z80 offered many improvements over the 8080 SAD Smiley 7, an enhanced instruction set including a more logical, comprehensible and readable system of assembler instruction mnemonics. More flexible 16-bit data movement, load, or LD, instructions, crucially including the stack pointer SP. More flexible addressing modes for input/output to eternal peripheral ports. Single-bit addressing of all registers and memory including bit testing. Shifts forward/rotates on memory and registers other than the accumulator. Improved and more accurate than the previous 8080 BCD arithmetic. Rotate instructions for BCD number strings in memory. 16-bit subtraction and 8-bit negation. Program looping. Program counter relative jumps. Block copy. Block input/output, I/O, and byte search instructions. 10. An overflow flag with better support for signed 8 and 16-bit arithmetics. V. New 9 and IY index registers with instructions for direct base and offset addressing. A better interrupt system, a more automatic and general vectorized interrupt system, Mode 2, primarily intended for Zilog's line of counter-forward/timers, DMA and communications controllers, as well as a fixed vector interrupt system, Mode 1, for simple systems with minimal hardware, with Mode 0 being the 8080 compatible mode. 11. A non-maskable interrupt, NMI, which can be used to respond to power-down situations or other high-priority events, and allowing a minimalistic Z80 system to easily implement a two-level interrupt scheme in Mode 1. A complete duplicate register file, 12, which could be quickly switched to speed up response to interrupts such as fast asynchronous event handlers or a multitasking dispatcher. Although they were not intended as extra registers for general code, they were nevertheless used that way in some applications. 6. Less hardware required for power supply, clock generation and interface to memory and I/O. Single 5-volt power supply. The 8080 needed -5V/+5V/+12V. Single-phase 5-volt clock. The 8080 needed a high amplitude, 9 to 12 volt, non-overlapping two-phase clock. Built-in drum refresh that would otherwise require external circuitry, and less SRAM, more expensive and less dense, but faster, was used. 7. Non-multiplexed buses. The 8080 had state signals multiplexed onto the data bus. A special reset function which clears only the program counter so that a single Z80 CPU could be used in a development system such as an in-circuit emulator. 13. The Z80 took over from the 8080 and its offspring, the 8085, in the processor market. 14. And became one of the most popular and widely used 8-bit CPUs. 3. 4. Some organizations such as British Telecom remained loyal to the 8085 for embedded applications owing to their familiarity with it, and to its on-chip serial interface and interrupt architecture. Likewise, Zenith Data Systems paired the 8085 with the 16-bit Intel 8088 in its first MS-DOS computer, the Zenith Z100. Despite having previous experience with its pioneering Z80-based Heathkit H89 and Zenith Z89 products. However, other computers were made integrating the Z80 with other CPUs. The Radio Shack TRS-80 Model 16 with a Motorola 68000, the DEC Rainbow with an 8088, and the Commodore 128 with a MOS 8502. Zilog was late producing a low-power Z80 suitable for the growing laptop computer market of the early 1980s. Intel produced a CMOS 8085, ATC85, used in battery-powered portable computers, such as the Kyocera-designed laptop from April 1983, also sold by Tandy, as TRS-80 Model 100, Olivetti, and NEC. In following years, however, CMOS versions of the Z80, from both Zilog and Japanese manufacturers, would dominate this market as well, in products such as the Amstrad NC100, Cambridge Z88 and Tandison WP2. Perhaps a key to the initial success of the Z80 was the built-in drum refresh, at least in markets such as CP/M and other office and home computers. Most Z80 embedded systems use static RAM that do not need refresh. It may also have been its minimalistic two-level interrupt system, or conversely, its general multi-level daisy chain interrupt system useful in servicing multiple Z80 I/O chips. All features that allowed systems to be built with less support hardware and simpler circuit board layout. However, Others claim its popularity was due to the duplicated registers that allowed fast context switches or more efficient processing of things like floating point math compared to 8-bit CPUs with fewer registers. The Z80 can keep several such numbers internally, using HLHL, DDA and BCBC as 32 bits registers, avoiding having to access steam from slower RAM during computation. 15. For the original MOS design, the specified upper clock frequency limit increased successively from the introductory 2.5 MHz, via the well-known 4 MHz, Z80O, up to 6, Z80B, and 8 MHz, Z80H. 16, 17. The NMOS version has been produced as a 10 MHz part since the late 1980s. CMOS versions were developed with specified upper frequency limits ranging from 4 MHz up to 20 MHz for the version sold today. The CMOS versions allowed low power standby with internal state retained, having no lower frequency limit. 8. The fully compatible derivatives HD64180/Z180, 18, 19, and EZ80 are currently specified for up to 33 and 50 MHz respectively. Design, programming model and register set. An approximate block diagram of the Z80. There is no dedicated adder for offsets or separate incrementer for R, and no need for more than a single 16-bit temporary register WZ, although the incrementer latches are also used as a 16-bit temporary register, in other contexts. It is the PC and IR registers that are placed in a separate group, with a detachable bus segment, to allow updates of these registers in parallel with the main register bank. 20. The programming model and register set of the Z80 are fairly conventional, ultimately based on the register structure of the data point 2200. The Z80 was designed as an extension of the Intel 8080, created by the same engineers, which in turn was an extension of the 8008. The 8008 was basically a PMOS implementation of Fetal-based CPU of the data point 2200.9. The 2200 design allowed 8-bit registers H and L, high and low, to be paired into a 16-bit address register HL.X, in the 8080. This pairing was added to the BC and DA pairs as well, while HL was generalized to allow use as a 16-bit accumulator, not just an address register. The 8080 also introduced the important 8-bit immediate editor mode for accumulator operations, and immediate 16-bit data for HL, BC and DA loads. Furthermore, direct 16-bit copying between HL and memory was now possible, using a direct address. The Z80 orthogonalized this further by making all 16-bit register pairs, including 9 and IY, more general purpose, as well as allowing 16-bit copying directly to and from memory for all of the SIA pairs. The 16-bit 9 and IY registers in the Z80 are primarily intended as base address registers, where a particular instruction supplies a constant offset that is added to the previous values, but they are also usable as 16-bit accumulators, among other things. A limitation is that all operand references involving 9 or IY require an extra instruction prefix byte, adding at least 4 clock cycles over the timing of an instruction using HL instead. This sometimes makes using 9 or IY less efficient than a method using only the 8080 model registers. The Z80 also introduced a new signed overflow flag and complemented fairly simple 16-bit arithmetics of the 8080 with dedicated instructions for signed 16-bit arithmetics. The 8080 compatible registers F, BC, DA, HL are duplicated as a separate register file in the Z80. 21, where the processor can quickly, 40 states, the least possible execution time for any Z80 instruction, switch from one bank to the other winking sad smiley 22, a feature useful for speeding up responses to single level, high priority interrupts. A similar feature was present in the 2200, but was never implemented at Intel. The dual register set is very useful in the embedded role, as it improves interrupt handling performance, but found widespread use in the personal